Last time we started with the addition formula for sine and cosine, and we derived the double angle formulas. This time we're going to start with the double angle formulas and get some other identities that turn out to be pretty useful. So here's the double angle formula for cosine, well, one of the three flavors of the double angle formula for cosine. And sometimes, in some contexts, which really means in calculus class, you have a cosine squared and you'd really rather have a 2 inside of your cosine. In other words, we'd like to replace a cosine squared with something that has cosine 2 theta in it. And we can do that if we just take this double angle identity and solve it for cosine squared. So let's see, start by adding 1 to both sides. We get cosine 2 theta equals 2 times cosine squared theta, and then divide both sides by 2. I forgot my plus 1 here. I need to squeeze a plus 1 in there. Okay. On the right hand side, the 2's cancel, and we just get cosine squared theta. And on the left hand side, we get 1/2 cosine 2 theta plus 1. And usually, there's no real reason for this, but usually I write the 1 first. So 1/2 1 plus cosine 2 theta equals cosine squared theta. All right, so this identity, it is useful in calculus, but until you get to calculus, it's actually not that useful, I don't think. But what we can do is take square roots on both sides. And we get an identity that is sort of the opposite of a double angle identity. So on the right-hand side, we're just left with cosine theta. And on the left-hand side, well, there was a square root, so we'd better write plus or minus. Plus or minus the square root of 1/2 1 plus cosine 2 theta. Now this still looks like some sort of weird double angle identity because there's theta and 2 theta. But if we just replace theta with alpha over 2, then something interesting happens. So I'm just inventing a new angle, or I'm declaring that theta has actually always been half of the angle we really wanted. So theta is alpha over 2. That means that 2 theta is just alpha. If you take the first substitution equation and multiply both sides by 2, you get 2 theta equals alpha. And if we use this substitution to change this identity, we get plus or minus the square root of 1/2 1 plus cosine of 2 theta. But remember, 2 theta is alpha. And then on the right-hand side, we get cosine of theta, which is alpha over 2. So this identity, this is called a half-angle identity. It tells you what cosine of half of an angle is in terms of the cosine of the original angle. It's a little bit weird that there's this plus or minus here, but as we will see, that plus or minus really does need to be there. There's no way around having that plus or minus there. You might suspect, hey, this all came from the double angle formula for cosine way up here at the top, and there was a flavor of the double angle formula for cosine that only had sine squared in it. Could we do this whole thing to get a half angle formula for sine? And the answer is yes, of course. I'm so glad you asked. So let's do the whole thing again, but starting with the double angle formula for the flavor of the double angle formula for cosine that has sine squared in it. So that identity looked like this. Let's solve this equation for sine squared. I'm going to do this in a slightly different way. Let's add 2 sine squared theta to both sides. And at the same time, let's subtract cosine 2 theta from both sides. And when we do that, on the left-hand side, the cosine 2 thetas cancel. And on the right-hand side, the 2 sine squareds cancel. So we're left with, on the left, 2 sine squared theta. And on the right, 1 minus cosine 2 theta. Oops, I missed my 2. There we go. Now we need to divide both sides by 2. And we get sine squared theta equals 1/2 1 minus cosine 2 theta. And there is a square formula for sine, just like we got for cosine. Notice that the right-hand side is the same as the square formula for cosine, except for cosine there was a plus there, but the sine version has a minus there. Okay, now we can get a half angle formula by taking square roots on both sides. And on the left we get sine squared theta. And on the right we get plus or minus the square root of 1/2 times 1 minus cosine 2 theta. Okay, and remember the trick for getting our half angle formula was to make a little substitution. We are going to declare that theta is actually alpha over 2, and that means that 2 theta is alpha. Oh, and I notice right here I have a squared that shouldn't be there. We took a square root to get rid of that square. Okay, so now we can make a substitution, and we get sine of alpha over 2 is equal to plus or minus the square root of 1/2 1 minus cosine of 2 theta, but remember 2 theta is just alpha. And there is a half angle formula for sine. So now that we have these half angle formulas, let's see what we can do with them. We'll look at 2 examples. Here's the first example. We're going to find the cosine of pi over 8 and the cosine of 9 pi over 8 exactly. And this, as we've seen in the past, this word right here, exactly, is key. We won't be satisfied by just plugging these angles into a calculator and seeing what it spits out. I want an exact expression for these values. Okay, so let's start with pi over 8. And when we work with pi over 8, this is half of a nice angle. Right? Pi over 8 is pi over 4, which is a nice angle, but divided by 2. Now it's starting to look like something that's coming from a half angle identity. Okay, so let's see. Cosine pi over 8 is cosine of pi over 4 over 2. And now if you look at the half angle identity for cosine, it looks like pi over 4 is playing the role of alpha in the half angle identity for cosine. So let's use the half angle identity for cosine with alpha equal to pi over 4. We get plus or minus the square root of 1/2 times 1 plus cosine of alpha, which is pi over 4. And let's simplify this a bit. It's the square root of 1/2 1 plus cosine pi over 4 is the square root of 2 over 2. And then if we simplify this whole mess, 1 plus the square root of 2 over 2, turns out it is 2 plus root 2 over 2. And then we're multiplying that by a half, so that changes this denominator into a 4. And then we can split the numerator and denominator up. in different square roots. So in the numerator, we get the square root of 2 plus root 2. And in the denominator, we get the square root of 4, which is 2. All right, so the cosine of pi over 8 is plus or minus the square root of 2 plus root 2 over 2. But wait, there's a problem. Cosine of pi over 8 should be a certain number, just one number. Why did we get 2? We get a plus or a minus. That can't be right. It's either one or the other. But the identity, the half-angle identity, doesn't know which sign to pick. We have to pick the appropriate sign because we know a little bit more than the half-angle identity does. We know that the angle we started with is pi over 8. And pi over 8 is in which quadrant? That's quadrant 1. And in quadrant 1, cosine is positive. So over here, where we have a plus or a minus, we're going to keep the plus and discard the minus. Okay? So we had to choose the appropriate sign here. The identity does not tell us which sign is correct. Okay, so now let's try this whole game with cosine 9 pi over 8. Well, look, this denominator over 8, that should be coming from a denominator 4, just like last time. So this is cosine of 9 pi over 4 over 2. So this time, alpha is being played, the role of alpha is being played by 9 pi over 4. So we can use the half-angle identity for cosine. Plus or minus the square root of 1/2 times 1 plus cosine of 9 pi over 4. Okay, and just like last time, cosine 9 pi over 4 is the square root of 2 over 2. So this is plus or minus. Now this whole square root, it looks exactly like last time because this cosine part, the 9 pi over 4, is square root of 2 over 2, just like it was last time. So we can do all that algebra to simplify the result. It's the square root of 2 plus root 2 over 2. But again, we have to choose the appropriate sign here. So what quadrant is 9 pi over 8 in? Let's see, 9 pi over 8, that's a little bit bigger than 8 pi over 8, which is a half turn. So 9 pi over 8 looks something like this. 9 pi over 8 is in quadrant 3. And since we're in quadrant 3, we need to pick the negative instead of the positive. Okay? So you can sort of see why the half-angle identity doesn't know which sign to pick. It's because it only saw this pi over 4. Well, it only sees cosine of pi over 4. And it can't distinguish cosine of pi over 4 from cosine of 9 pi over 4. Right? Because cosine is periodic. Those two angles differ by 2 pi, and so once you take cosine, you can't tell the difference between them. So for this reason, the half-angle identity really does not know which sign to pick, the plus or the minus. And so you have to pick the appropriate sign when you're using the half-angle identity. All right, so let's look at a second example. Let's use this diagram to find sine of alpha over 2. Okay, well, sine is going to be opposite over hypotenuse, so or y over radius in this diagram, except this diagram is a diagram for alpha and not for alpha over 2. So we know information about alpha, not alpha over 2. We had better rewrite sine alpha over 2 in terms of just alpha. Of course, the half-angle identity for alpha for sine will let us do exactly that. So it's plus or minus the square root of 1/2 times 1 minus cosine of alpha. So there's the half-angle identity for sine. And it looks like, since the half-angle identity for sine has cosine of alpha in it, it looks like we're going to have to figure out the cosine of alpha instead of the sine of alpha. So we need to use the Pythagorean theorem to figure out what this bottom side is. And of course, we're looking at a 3, 4, 5 triangle here. So square root of 5 squared minus 4 squared, that turns out to be 3. But because we are in the second, alpha is in the second quadrant, this had better be negative. Okay. So now we can use this diagram to write down the cosine of alpha. So we get plus or minus the square root of 1/2 1 minus cosine alpha. And according to this diagram, cosine of alpha is negative 3/5. All right, so plus or minus the square root of, let's see, 1 plus 3√5, that's 1 plus 3/5, that's 5/5 plus 3/5 is 8/5 times 1/2 is 4/5. So we get plus or minus 2/√5. Or if you like to rationalize your denominator, 2√5/5. Okay, so what about the plus and the minus? Do we have enough information to figure out what quadrant alpha over 2 is in? Let's see. Well, alpha is going clockwise and is in the third quadrant. So if you draw a really rough sketch of where alpha over 2 must be, it's going to be something like this. Okay. So it's in the third quadrant. And if you play around with it a little bit, you'll see that no matter where alpha is in the second quadrant, alpha over 2 is always going to end up in the third quadrant. So since alpha over 2 is in the third quadrant, sine of alpha over 2 must be negative. So we're going to keep the negative and discard the positive. So negative 2√5/5. And that's it. So with the half-angle identities, be extremely careful about that plus or minus. Usually in applications, you do have enough information to determine whether you need the plus or the minus possibility for the half-angle identities. So be sure to make the appropriate choice.